So hello everyone, thank you for coming to this seminar. My name is Madi. Today I'm going to talk about how to control distributed energy resources. So we're gonna talk about how to control distributed energy resources in islanded AC microgrids. And in islanded mode, microgrids are disconnected from the bulk grid, which means that voltage and frequency of the microgrid are no longer supported by the bulk grid. And typically, distributed energy resources are interfaced with power electronics, which means that microgrids have low or no rotational inertia. And because of the low level of rotational inertia, frequency dynamics are much faster in microgrids than in the bulk grid, and frequency deviations are typically larger. So this means that traditional frequency control schemes cannot be used in microgrids because they are too slow. So practitioners, when they talk about secondary frequency controllers, they treat DRs with interface with power electronics as controllable voltage sources with adjustable frequency and voltage. This allows us to simplify the microgrid model, and in this case, after linearizing the power flow equations and fixing the loads and fixing the voltages, we obtain this ODE model, which is very simple relationship between the inverter injections and the frequencies. And matrix S at the equilibrium point has some nice properties. If the phase angle difference across each line is bounded by some bounds, which depend on the line susceptances and conductances. So we're going to use this model throughout this work. And regarding the communications network, we choose distributed architecture because it's resilient to a single point of failure. Centralized architecture, it requires communications over prohibitively large distances. And it's more difficult to tune parameters of the centralized controller than that of the distributed controller. So frequency control design will be based on the concepts from multi-agent optimization. And in the first and the next, in this slide, next slide, I'm going to give some short background information on multi-agent optimization. And in the multi-agent optimization, the problem can be formulated as follows. Consider n agents. Each agent has its local cost, which is unknown to other agents. And two agents can communicate with each other if they are physically close. Okay? And collectively, they try to minimize the total cost. Now, one common approach to solve this optimization problem is to let each agent estimate the solution of this problem using, for example, gradient descent. And then neighbors, they average their estimates via communications. And typically, this approach includes two steps. Averaging step ensures that estimates of the agents converge to a common point. And then the gradient descent step steers this common point to towards the optimal set. And there are several techniques for solving this problem. And for undirected communication graph, where the communication links are bidirectional, one approach would be to use distributed subgradient method. And in the distributed subgradient method, agent I needs to execute this iteration where this first term is distributed averaging term, in which each node I is basically computing weighted average of its own estimate and the estimates of its neighbors. And then there is this gradient descent step. And note that these weights are time varying. So if node I does not receive any information from node J, then this the corresponding weight Aij will be set to 0, right? And the weights, because we are computing weighted average, the weights need to sum up to 1, right? Now, if we apply this method to solve multi-agent optimization problem over directed communication graph, we will face one issue. And the issue is that some nodes which are more centrally placed in the network or more strongly connected to the network, they tend to be more influential than other nodes. They end up putting more weight on the information. So to cancel out, and that will result in bias in averaging. And to cancel out the bias in averaging, we should use this ratio. Each node needs to maintain the ratio of these two variables to compute x. And this is called subgradient push method. It has more complicated algorithm for performing distributed averaging step. And it has also this gradient descent step. Now, control objectives, which are to achieve desired load sharing among generators and maintain frequency at 60 Hertz. These control objectives can be formulated as multi-agent optimization problem. And to solve this problem, closed-loop microgrid dynamics with included primary and secondary frequency controllers, they need to solve this multi-agent optimization problem where each generator has this local cost, which is just a square difference between its its power output and desired power output, which is just a participation factor determined by the tertiary control layer times the total load plus the losses. Now, to better understand information from the previous slides, let's look into distributed averaging PI controller, which was proposed a couple of years ago. And in this controller, frequencies are adjusted such that the injections of the inverters track the set points, and then the set points are adjusted so as to eliminate the frequency error and achieve load sharing. And here we have this Laplacian matrix, and basically we are computing some kind of weighted average of the estimates of the generators. And if we look at the closed-loop microgrid dynamics induced by this controller, we can see that the frequency error term can be viewed as if you're performing gradient descent step, and load sharing can be viewed as if you're performing distributed averaging step. Right? So, is it clear? So Xi is some kind of estimates maintained at each generator, and we'll talk about it in the next slides. Communication network used by this controller assumes that communication links are bidirectional, meaning neighbors exchange information with each other, and then the information exchange is simultaneous. If they exchange information, that happens within the same period of time, within the same sampling period. So it's a simultaneous information exchange. And that information exchange happens at each iteration. And all this and such communication network can be difficult to realize in practice because of the packet drops, communication delays. Practical communication network is time varying. Way to resolve communication delays is to let neighbors average their estimates whenever they exchange information. So if agents I and J exchange information during this time interval, then they set the weights in the Laplacian matrix to some positive value. If they don't exchange, then they set to 0. And then agents need to recompute diagonal entries of the Laplacian matrix, and they do that locally. And this is for ensuring that this matrix here is doubly stochastic matrix. And this recomputation of the weights will lead us to these iterations. These iterations are the same as the ones from the previous slide. The only difference is this time-varying Laplacian matrix. Now weighted averaging is time-varying, basically. Each node is computing the weighted average of the estimates which it has received. There might be a case when agent does not receive anything from its neighbors, then all weights will be 0 except diagonal entry, which will be set 1, which basically means that weighted average will be just agent I's estimate. And unfortunately, there is still a limitation. We're still assuming that information exchange, when it happens within the same sampling period. Any questions? So quiet. Yes.
Question. So when you say it's time varying, so basically you're saying that in the process when it's solving this problem, it detects basically the neighbors that can communicate with the changes accordingly. Is that what you mean when you say time varying?
Time varying meaning that agent I may not receive any information from other neighbors at any given iteration. So if it does not receive any information, then it needs to recompute the weights of the averaging step. Yes. But previously, in this previous slide, it was a perfect communication, right? Like information exchange happens at each iteration. But here we're looking at more time-varying network.
What's the time step between iterations?
I mean, this is very, it can be 20 milliseconds. Typically, it's like that. Yeah. So for directed communication graphs, when we have unidirectional communication links, when we can apply the subgradient push method that we have introduced earlier to design frequency control. So these are the same iterations as before, but the only difference is how we're computing this Xi variable. And Xi, again, we are using this ratio of these two variables. Now, one assumption that I haven't mentioned is that each node J needs to know its out degree. And out degree here is the number of agents which have received information from node J. And this quantity is time varying, right? But in practice, DJK can be set to the total number of neighbors of agent J. And converges with high probability. And let's look at the multi-agent interpretations for frequency control. This is the same optimization problem that we had earlier, but it's rewritten in terms of different variables, and these variables are just scaled versions of the injections, and this quantity, which again is total load plus losses divided by the sum of the Drup coefficients of the frequency controller. And assuming P tilde star and zeta star is solution of this problem, we can make the following observation that psi ik is agent I estimate of zeta star, and P tilde, which is scaled version of the injections, is basically, using the jargon for multi-agent optimization, is the average process induced in microgrid. So it's basically the average estimate of P tilde star over the inverter nodes. Now, if we go back to undirected case, the problem was that we had to assume simultaneous information exchange. So when node 1 and 2 perform averaging, they have to do it at the same iteration, right? Now here we propose another method which overcomes this limitation here, and in this method, we basically let each node maintain one estimate for each communication link. Instead of maintaining only one estimate of zeta star, we maintain, for example, in this case, node 1 maintains two estimates. One estimate for link 1,2, and the other estimate for link 1,3. Okay, and note that the estimate which corresponds to link 1,2 is updated by performing averaging with only node 2. It doesn't perform averaging with node 3. And here, similarly, we have averaging with node 3, but we don't perform averaging with node 2. Okay. But of course, since all these estimates are estimating one quantity, zeta star, we still need to perform local averaging. And we do perform local averaging through gradient descent step. So we add additional gradient terms into gradient descent step to drive all local estimates of node 1 in this case to a common value. Any questions about this? And then here we use an alternating averaging, which means that when node 1 receives information from node 2, it performs averaging, and node 2 waits for node 1 to complete the averaging. And then node 2 performs averaging, and node 1 waits. And this alternating averaging can be implemented through a very simple message passing protocol. Okay, no questions? So we talked about the local averaging, right, happening at node 1, and we said that we're gonna add local averaging objective into gradient descent step, and that can be done by adding this additional objective. So this is what we had before, and in this method we are adding this additional objective which performs local average. Yeah. Quite. Okay, so now the next slide basically formalizes what we have said in the previous slides. So here node I and J, they maintain two estimates for communication link IJ, we call ZIJ and ZJI, and they, when they perform averaging, they do it in alternating fashion, and at each step, at each iteration, they perform gradient descent, which includes this frequency regulation, frequency error term, and then this local averaging objective. And then this is the closed loop dynamics induced by these iterations. And mathematically, here in this work, we're assuming that the network is lossy, but when for convergence analysis works for the lossless case. We still don't have convergence analysis for the more general lossy case. And it's because of this matrix S. For lossy case, matrix S is non-symmetrical, and that makes convergence analysis a bit harder. Okay, and the message passing protocol for alternating averaging, very simple. We consider link IJ, and we let node I maintain acknowledgement variable, new IJ. When node I receives a new and different value of new J, different from the previous step from J, this means that J has performed averaging, okay, when it receives this value from J. And then node I needs to execute 3 steps. Node I needs to perform averaging, and then it needs to send new IJ to a different value to let node J know that node I has performed averaging. And it sends ZIJ and new IJ to node J. And it's simple message protocol with acknowledgement, flag. I haven't put together the simulation results, so I'm gonna just skip it. And in conclusion, so we introduce frequency controllers over time-varying communication graphs, and we propose this new distributed scale subgradient method, which doesn't only work for power systems, it works for general multi-agent optimization. And it overcomes this limitation. Information exchange does not have to be simultaneous, and it handles when there are packet drops. It doesn't assume that you need to know your out degree like it was in the subgradient push method. Yeah.
You say for a lossy network, the solution doesn't converge?
No, we don't have proof, mathematical proof.
Do you still see it converge?
Actually, I haven't played yet for lossy case, but I'm pretty sure it will converge. Because this the API controller, that distributed averaging controller, converges for lossy network. Yeah.
So you say like converge means the whatever you command will be tracked perfectly?
Yes. So meaning that generator power outputs, they share the load in accordance with the participation factors. Yeah. Even if you have losses, and your frequency will be at 60 hertz at steady state.
How fast can it converge back to 60 hertz?
This is faster than AGC.
But how?
I don't know, but there are like convergence analysis which depend on how
many iterations does it take?
So this is the like a first order gradient descent, right? So it converges linearly, I would say, exponentially fast.
You said it converges with high probability.
Yeah.
So what are the other probabilities that you assume?
Can you remind me which probability?
I don't remember exactly which of the algorithms you were.
Here's the out degree, yes. Yeah, so surprisingly, even when you set this out degree to some fixed quantity, like the number of neighbors, the total number of neighbors for H and J, this converges. Yeah. But there is no proof for that, but in simulation it converges.
The time variant case, I'm trying to understand what makes the problem more complicated, because you said in the time variant case, what happens is that it detects the neighbors that you can communicate with, and as a result, it changes out degree accordingly, right?
It's difficult to compute out degree. Impossible.
Is it?
Yeah, impossible. How can you know how many agents received information that you have sent?
Oh no, but the other way around though.
No, this is not the other way around. So this quantity is the number of agents which have received information from you.
What if you send an intelligent signal, the node that receives?
That's gonna slow down your algorithm, right? So we don't want to increase the sampling period. Okay, so that's it. And if you are interested, I can send you the manuscript for the paper.
Oh, so click. Did you lose it? Oops. No, I think you gotta click this guy. One over. Yeah. And then you'll have to change the display. Yeah. Good. Does it turn this thing on or anything? It's recording, right? Yeah, right? Okay. Okay. Thank you for coming today. So the title of my talk is Modified Ripple Correlation Control for Predictable Off-Maximum PowerPoint Tracking. So here's just the outline. It's basically separated into three sections. The first is just a general overview of why we're trying to do this. Then an intro to ripple correlation control, and then the two things we're trying to add into ripple correlation control, which is essentially increasing the switching frequency, and then modifying the algorithms to be able to track off maximum power point set points. Off maximum power point set points. That's a tongue twister. Okay, so the standard array control is obviously maximum power point tracking, which just tracks the maximum power you can get out of the sun at any given moment. From an energy production view, this is always the best case because you're maximizing your energy production. But from a variability viewpoint, this also maximizes your variability because you can think you're just tracking whatever the sun's doing. So in our current situation, that's fine because variability out of a solar array is not really penalized like by a utility or the government. But in the future, as solar capacity increases, we could begin to see like restrictions placed on arrays. So our question is, in an array where variability has some sort of realized cost, is operating at maximum power point the best economic choice? And then this is, again, just a summary, but we've shown before that if variability is a choice, then as soon as you move off maximum power point, you add in an additional degree of freedom kind of into your optimize or into your control scheme. And as soon as you do that, then you could show that if you're trying to optimize a certain variable that isn't just energy production. So if it's energy production plus variability, energy production plus your storage size, then as soon as you do that, off maximum power point becomes more optimal than just tracking the sun. So this is just showing like a simple example. So say you are have an array that's heavily penalized for having a lot of variability. And depending on the size of the storage system you've had, you'd want to track a different set point throughout the day. So the gray here is just showing how the maximum power point tracks throughout the day. So if you don't have any battery, then you want to be really conservative with your set point and kind of track the bottom envelope, where if you do have a storage, you can track middle or be more aggressive. You'd have to run the numbers to see which one, of course, is optimal, because it depends on how much the storage system costs and stuff. But once you have the set point, then you have that additional degree. So that's the background. And then, so now we're looking at ways to actually implement basically a set point algorithm. And we're trying to do that with ripple correlation control. So ripple correlation control is, for those who don't know, it's just a maximum power point tracking scheme that utilizes the switching inherent in the converter to A, tell you where you are on an IV curve, and B, drive you towards the maximum power point. So for those who really don't know, I guess, all solar PV panels and arrays have an IV curve, which is a one-to-one mapping of their current and voltage. And then they have a single, without one, they don't have bypass diodes, but then they have a single maximum power point. So what ripple correlation does is that it uses the switching inherent in the converter. So you can think when this converter switches, this inductor will have a current ripple on it, and that current ripple will be imposed on the panel. When that current ripple is imposed on the panel, then you'll have a current ripple this way, or this way on the current, which will move you somewhere on this curve. So ripple correlation control uses the derivative terms to drive to tell you where you are on the curve and then drive you to the maximum power point. So you can think of the derivative terms as just telling you whether or not that value is increasing or decreasing. So this is showing a voltage-based ripple correlation control for a boost converter, where it just uses the derivative of the power coming out of the panel and derivative of the voltage. So when you're moving towards the maximum power point, your power is always increasing, so you'd have a positive derivative. And when you're moving away from the maximum power point, you always have a negative. Your power is decreasing, so you have a negative derivative. And then with the voltage, when you're moving left to right on the IV curve, you have a positive derivative. And when you're moving right to left, you have a negative. So with those just two premises, we can use this product term and determine just by basically the sign of it where we are on the IV curve. So if our product's negative, we know we're on the right side of the maximum power point, because one of our terms are basically 180 degrees out of phase. Whereas if our product term is positive, then we know we're on the left side of the maximum power point, because our terms should be more or less in phase. And then this crossover happens right around right on the maximum power point, where you cross from positive to negative. So yeah, this is it. So we have basically three regions of operation. We have one region where we're 180 degrees out of phase. Our product's always negative, so our integral drives one way, negative. Then we have another region of operation where our terms are in phase, our product's positive, and then we drive the other way. And then we have the final steady state value where our product terms are 90 degrees out of phase, and then the integral from an average standpoint doesn't go anywhere, because it increases and decreases to the same point over the same switching cycle. So, and this holds not just for 180 degrees out of phase or 0 degrees out of phase. Essentially, If your signals are between 90 and 180 degrees out of phase, their product will always be on average negative, so the integral will decrease, and vice versa for the other thing. The takeaway here, though, is that as you begin to lose phase off of either 180 degrees or off zero, your integral will increase or decrease at a much slower rate. So later I'll start showing where we can get some phase shifts introduced into our converter, and that will affect the time to convergence just for this manner. The integral term kind of goes to zero. So why does it matter? So PV arrays, so ideally we want our PV array to just operate on IPV and VPV, which are given by the IV curve and have that 1-to-1 ratio. But PV arrays have well-known capacitive effects due to their PN junctions. It's essentially just a diffusion capacitance, which will introduce this third or the second effect here that at low frequency isn't really an issue, but at high frequency it can begin to decouple your measured current seen by your converter with the desired current coming out of the panel. It's just given by this simple equation here. So the takeaway here, the converter only sees the measured current times the measured voltage, which in this case we're just saying is VPV. But and it's kind of hoping that that's as close to the actual PV current and PV voltage as possible. So if we want to look at the effects of the power and voltage ripple as a function or from the capacitor, then we can, just using the simple power equation from the previous slide, linearize it with respect to the voltage and the current seen by the converter using, this is just a first order model. And then once you simplify that, you can solve for the two ripple terms, and you get this equation here. So there's three terms here. The first two are the desired terms. These are just basically, if you look here, it's just the derivative of the power with respect to the voltage. But then you have this third term here, which is the capacitive effects added in. Then if we look at how the capacitive effects set our phase as a function of switching frequency and where you are on the IV curve, we can see that as low frequency, we just have our pretty desired behavior, where if we're to the right of the maximum power point, we have 180 degrees out of phase, and where if we're to the left, then we have zero, we are essentially in phase. But as the frequency increases, we get this capacitive term starts to dominate, and then all of our points converge to this -90 here. So the problem there is that it will still, the converter should still work technically as long as there's just a little bit of phase, but it becomes harder and harder to differentiate points as everything converges to 95 degrees. So you can just think of it as here you have 0 to 90 degrees to work with, whereas here you have maybe like 95 to 90, only 5 degrees. Does anyone have any questions before? Nope. Okay. Okay, so what we're proposing is that we want to add in a capacitive compensation term given here into our measured current to estimate the actual PV current coming out of the panel. So we already have access to the voltage derivative just due to regular RCC control. So we just take our measured current IS, add in the compensation term, and the goal is to negate as much of the capacitive or the parasitic capacitive current as possible. So then when we add that back into our linearized model, we get this equation here, which obviously if these two terms are equal, then they'll completely negate themselves. So that's probably not going to happen in real life, because this value does have can change with the voltage on the panel. But we're showing here on the right, so this is the simulation of this model right here, that even if you're within the ballpark of the estimated capacitance term, you can kind of greatly increase the phase available at higher switch-in frequency. So if you follow, say, the 75% estimate at, say, 100 kilohertz, so you go from this line here to this line when you're on the left side of the maximum power point, and you add about 30 degrees of phase when you're on the right. Okay. So I built a little boost converter and added in this compensation with a ripple correlation control. And here I'm just showing how the phase compensation is actually working. So I've just set the duty ratio to a high value, which forces the operating point to be to the left of the maximum power point. So this is on the high current side of the IV curve. And if you remember, we are expecting our voltage and our power derivatives to be in phase at this point. But we can see that their product term has this positive and negative periodic effect, which you would get as those two terms move towards 90 degrees out of phase instead of the 0 degrees that we want. So this is the uncompensated product of the derivatives, and then this is the compensated where that essentially this negative portion was removed. And this, so just like kind of as an addition, the compensated converter is stable at 100 kilohertz, and the uncompensated one isn't. Okay, so that's just the capacitive compensation part of the presentation. Anyone questions? No? Okay, so moving into, now we just wanted to look at ways to kind of modify the RCC algorithm to allow for following a set point that's not necessarily the maximum power point. So, and I'm just going to propose a couple models that we want to try to implement in hardware in the future. So the first one is just switching between a ripple correlation control and a current mode control, where essentially you find the maximum power point values with the ripple correlation control, and then you switch to a current mode control to operate to the right of the maximum power point in this constant voltage variable current region. And then you would periodically recheck the maximum power point to make sure it hasn't changed. And this is probably the simplest off maximum power point control that you have, because it's simple to implement, and it's, so just the pros and the cons, I guess. It's simple to implement and static through up transients. So an up transient's where like an array is shaded and then a cloud moves off the array. So if you're worried about variability, then you have to worry about the up and down transient. So if the cloud moves off the array, the power will jump up. Whereas if a cloud moves on the array, then the power jumps down. Both are undesirable. So it's static through up transient since it just tracks the current. And then you can implement it so that it just follows the maximum power point on down transients. So that just kind of limits the damage as much as possible. The cons of this is that it saturates the ripple correlation controller when it's in current mode control, which means that when you switch between the two, you'll have to spend some time getting rid of that excess energy in your integrator. Okay, the next one is just modified RCC1, and this is, we're proposing you can introduce kind of a virtual local maximum on the right side of the IV curve by just flipping the sign of the power derivative about like a certain reference current. So in this region, in this region, and this region, you have regular ripple correlation control, and then in this region, between IREF and the maximum power point, you just flip the sign of the power derivative, and that makes this point kind of the region of the traction and not the maximum power point. So before, as you're moving this way from like here to here, you'd have a positive derivative, but when you flip it, then you'd move back. So you have positive, negative, or positive, positive, and then this would be negative, and this would be negative. So the pros, I guess, of this model is that it works within the RCC controller, so you can quickly turn it on and off. And it's like the other one, it's static through the up and down, or static through the up transients, and it follows the maximum power point on the down transients. The cons of it is that because you're basing kind of like your local maximum on a current reference, that this can shift around if you have poor tracking, and that will put some like wiggle in your set point. And then the last one is just adding a constant DC value into our integrator. So if you remember before, to the right of the maximum power point, it integrates a negative value as long as the average here is negative. At maximum power point, the average is 0, and then on the left, the average is positive. So we can move that, so you can think of that steady state value as the steady state is wherever the average is 0. That's where you will end up and stop moving, or stop. That's where the integrator will end up. So you can add in this DC value, which will push your steady state to the right of the maximum power point if the beta value is positive, and it pushes you to the left of the maximum power point if it's negative. So again, the pros and cons, this is probably the simplest to implement, and it works within the RCC. The cons would be you would have to find some way to map beta to the set point power. So these are the 3 in simulation, which
wouldn't it just be some kind of PI controller, because that beta is going to shift with the solar on the array during that day?
that beta, yeah.
So,
Wait, say it again.
So it would be some kind of PID control on the array as a whole. Like you'd have a set point being desired power, and it would just have to follow. Like beta would be adjusted according to the set point power.
Yeah. Yeah, and then you can easily turn it on and off if you want to just kind of like go back to normal ripple correlation control. Or the nice thing about this one is that you can just set this value with like a microcontroller or something. Whereas with the other ones, if you're flipping power, you have to do that with like an op amp and then a switch and then a comparator. So this is just the simulation results of the 3 different algorithms. You can see when we switch, this is the current mode control, so when we switch from current mode to RCC, this is so the higher values, obviously the maximum power point. You have to get rid of that excess energy from it saturating, which causes these big spikes or transients in the power. And then these 2 do pretty well, though the one where you're flipping the signal of dp/dt seems to have a little more ripple in it, probably because you're messing with it's the maximum power point becomes basically a triangle at that point. It's not the kind of a graceful curve as you see in normal IV curves. And then just kind of lastly, an update strategy. So if you are off maximum power point, you have to check every now and then to see where, if the maximum power point changed so that you could update your values accordingly. So naturally occurring irradiance changes on like less than a 10 hertz rate. So you could just periodically check the maximum power point, see if it changed. And if your converter converges in under 5 milliseconds, and say you check 10 times a second, that's only 50 milliseconds. So you're spending 95% of your time at the set point. So it shouldn't like put a lot of transients on your output. Another way that we're proposing or looking into is to monitor the voltage derivative, because you can determine, even if you're like at a fixed set point, you can determine whether or not the IV curves changed by just tracking dV/dt. So if dV/dt is at a certain value and then all of a sudden becomes larger, you know you're just experienced a down ramp where now your IV curve's down here, and then you're in this variable voltage region of the curve, as opposed to this region where it's relatively constant. Or if dV/dt becomes smaller, you've just experienced an up ramp where you've gone from basically this point, where it's basically the vice versa. you've gone to a more constant region of the IV curve. That's just something we're looking into to add on. So in conclusion, the ability to track a predictable set point adds another degree into PV array control. And in order to do this in like a intelligent manner, because you could always just find the maximum power point, move off of it, and then just kind of say, or hope the radiance doesn't change while you're at that set point. But if you want to do it in a predictable manner so that you can actually follow your transients, you need to know where it is essentially all times. RCC is a good candidate for that because it has convergence tied to its switching frequency, and we showed that capacitive compensation can increase practical RTC switching frequency. And with that, I'll take any questions.
One question on slide number 19, you talk about using dB over dt. So for that, do you actually have to calculate dB over dt, or do you use something you figure out?
No, in ripple correlation control, you have to calculate the derivatives.
What are the strategies to calculate derivatives, because it could be affected by noise and media?
Yeah, that's a good question. So here we go. So yeah, you can't actually calculate a derivative, like you can only really approximate it. So you can approximate it with a high pass filter, where this is essentially, the numerator is essentially the derivative term times this RC constant, and then this pole on the bottom limits your high gain frequency over here to just R over C. So or else this would just keep going up with frequency. So if you have a little bit of noise at a high frequency in your circuit, it would cause your op amp to become unstable. The trouble here is that once you use like a practical differentiator, you have a trade-off here of noise gain and phase. So differentiators always have ideally a differentiator has a 90 degrees of phase shift. But once you put this pole in to limit the gain, you start to lose phase off of 90 degrees as the frequency increases. And so of course you can push this term further and further. You can push this pole further and further out, but then that would increase this gain. So it's a trade-off. Does that make sense?
Yeah. But would it affect the stability of your controller or anything because of the phase shift?
Yep. So if we add in the compensation term, we go from here to here, and it does affect. So now the high frequency behavior isn't actually tracking -90 anymore. It's tracking the phase difference between whatever the parasitic component is and our differentiator. So if we can keep that at a relatively low value, then we can still push our switching or push these kind of these transitions here, which are undesirable because now we're losing the phase we want. That's essentially this. But if we can push these out past our switching frequency, we can still increase the phase or the switching frequency of the converter. Any other questions?